Good morning. All right, today we're going to take a look at a lesson about how to write electron configurations, or sort of a review of a lesson about how to write electron configurations, taking that structure of the electron cloud and being able to represent it in kind of a shorthand that just has letters and numbers to it, rather than trying to write out giant bullseye diagrams or trying to write out orbital diagrams with circles and arrows, all that stuff. Just a way to summarize it down, because electron configurations are very useful for us to be able to make predictions about atomic behavior when it comes to chemical reactions. So this is kind of at the base of everything that we're doing today. So just kind of by way of review, remember that the electron cloud is definitely a lot fuzzier than we thought it was at first. It used to be just kind of this big old sort of nebulous area. We knew from Bohr's work that there was sublevels to it, or so I should say that there's energy levels to it. The energy levels are based on that idea of kind of distance from the nucleus, as well as just energy of those particular things. If you're jumping up to a higher energy level, you've got more energy that's got to be absorbed and then released as you're there. But largely, you can kind of think of it as terms of size, different shells like that. These are three-dimensional spaces, though, that are needing to be shared by a bunch of high-speed, very small mass objects known as electrons. So we used to think that an energy level was enough, and now we know that the energy level has to be broken down further into things called sublevels, and sublevels are related to three-dimensional shapes. So instead of just being a sphere, it's kind of the way that 2 or 6 or 18 or whatever electrons can share that general space, and how do they subdivide that? Well, that is called a sublevel. Furthermore, these sublevels have particular shapes that's associated with them, and you're familiar with some of these guys. Sublevels S, P, D, and F are the names of those sublevels. Each one of those sublevels is associated with a particular 3D shape. So for example, a sphere is what we associate with the idea of a simple S sublevel. P sublevels are a little crazier. They're more of a dumbbell shape, kind of like that, or it could be that direction, or it could be something else. That's where the three orbital places come into play. Ds are more complex yet in terms of having to subdivide even more space, and they're clover shapes. So kind of 1, 2, 3, 4, or I've heard them called fuzzy daisies, something along those lines, 1, 2, 3, 4, like that. And there's 5 different ways that those can be arranged. And then there's the Fs are just insane in terms of their shapes. There's a whole bunch of different shapes for them. Fuzzy, daisies with spikes and some other crazy stuff, things with donuts and all weirdness. So don't stress about them too much, but these are these different shapes that these things can be arranged into. Furthermore, we can then talk about, all right, well, how are electrons using these sublevels? Well, we call these orbitals. In our atomic apartment building diagram, we talked about the different bedrooms that these electrons were in, and the orbitals are simply the orientation of those shapes. So if a P consisted of 3 different fuzzy dumbbells, which fuzzy dumbbell is it? Is it this one? Is it this one? Or is it this one? That's all that the orbitals really represent in the real world. But again, we tend to talk about it in terms of are there 1, 3, 5, or 7 different possible orientations for those things. And the key thing here is to remember that each orbital can hold 2 and only 2 electrons. When we did orbital diagrams, we represented each orbital with a circle, and then we had arrows to represent each one, and there was only 2 arrows that could ever put in one particular circle. Okay, so moving forward from this, when we started to draw these out, we were drawing these energy levels, sublevels, and orbitals in a way that was a little bit easier than trying to draw 3-dimensional fuzzy spheres and fuzzy things with donuts on them and all this kind of craziness. So again, we used circles to represent the orbitals. Again, when we drew these, we had 1 circle for each orbital. So an S sublevel has 1 orbital, so it's 1 circle. A P sublevel had 3 different orbitals to it, so you had to draw the full set of 3 circles. And a D sublevel had a full set of 5 orbitals, so you had to 1, 2, 3, 4, 5, had to draw all 5 circles at the same time. Keep in mind that each energy level consists of a different number of sublevels. So the first energy level has 1 sublevel, S. The second energy level has 2 sublevels, S and P. Third energy level has 3 sublevels, S, P, and D. So the numbers of circles you have to draw for energy levels above 3 starts to get quite large. The next thing is that we started to fill in those circles with arrows to represent the different electrons and figure out which electrons were in which sublevel and which orbital. We used up down. That represents a quantity known as spin. We kind of called about it as top bunk and bottom bunk when we were joking about it, but there's 2 electrons that can fit in each orbital space, so there's the up arrow and the down arrow that went along with this. It is okay, and don't forget this is an important part of this, when you're drawing orbital diagrams, even though you have to draw a full set of circles, it is okay, in fact it's necessary, to sometimes have empty circles or to have half-filled circles. When you're doing particular orbital diagrams for elements, it's very common to have, say, a p sublevel, or sorry, a p orbital that doesn't have anything in it. So maybe there's something in the first circle, something in the second circle, but the third circle is empty. That's totally fine. In fact, that's absolutely correct. And then same thing when you're doing orbitals that you may only have one arrow in there. In fact, that's also an important bit. So let's take a look at an example here. Here's oxygen. And again, oxygen, when we're trying to figure out how to write the orbital diagram, this particular example has squares on it because it happened to be the one I found. It's a little easier to do squares on the computer. Typically, when we draw them, it's easier to draw circles, so that's why I encourage you to do that. And then you can see that oxygen has, if you look at the periodic table, or the one behind me, oxygen has 8 electrons. So the first 2 go over here in that first energy level. There's an up and a down arrow. Then the third electron goes over here in this 2s. Fourth one goes in the 2s as well, and that's now full. And then after that, we have to put the rest of them in the 2p sublevel. There's 3 orbitals for it, so that's why there's 3 boxes showing here. And when we fill these up, remember that we fill them up kind of going left to right. You always do 1 electron at a time, and then you go back and get the roommate. So the first of these went here, the second one went in the second box, third one in the third box, and then the last one went back and formed a roommate up here in that first of the 2p orbitals. So we would write this out in the end as 2 arrows, 2 arrows, 2 arrows, 1 and 1. And again, so the 1s is full, the 2s is full, and the 2p is only partially full. There's 2 empty spaces in there. So if you try to figure this out, writing electron configurations is a little bit easier than trying to write orbital diagrams. Orbital diagrams are, kind of a pain with all these circles and arrows. They're especially difficult to try to do on a computer. So when we're writing these out, they get really long. There's lots of circles everywhere. We wanted to develop, or scientists wanted to develop a summary way of discussing kind of what all these electrons were doing. Second thing is it's got almost the same information. Electron configurations and orbital diagrams have very similar information. The only difference being whether a pair is shared or unshared. And I'll give you an example of what that looks like here in just a second. It's the only thing that's really missing. But if you know what the electron configuration is, you can go back and draw that last little piece of that orbital diagram if that's something that you really need to know. There's always a pattern to doing electron configurations, and I'll go into that here in a little bit. You don't necessarily need to create an orbital diagram first, although you're welcome to do so. There's certainly nothing wrong with that. But once you figure out the pattern, there's definitely a variety of different shortcuts that you can use to make electron configuration drawing a lot faster and quicker. So here's oxygen's orbital diagram. Again, I just grabbed it from the previous page. And when we want to write an electron configuration for this, all we're going to do is we're going to get rid of basically the squares and the arrows, and we're going to replace them with his numbers and letters, basically. So I'm going to continue with writing the 1s, but instead of writing arrow, arrow, I'm going to use an exponent 2 to represent that there's 2 electrons there. Same thing with the 2s. Instead of having arrow, arrow, I'm going to write 2s and then an exponent of 2 again because there's 2 electrons in the 2s. And then for the 2p, I'm going to add all these guys together. I'm going to summarize. So I would write 2p, and instead of using a squared, I would have to write the number 4 because there's 4 electrons in there. So this is what it ends up looking like when we're done. Keep in mind what these different components are here. This first number that looks like a coefficient is the energy level. The letter represents the sublevel, which has orbitals to it. And then the little number up there, the exponent, is actually a representation of the number of electrons in that sublevel, the total number. So that's why we have 2s2, and then the last one is 2p4. This number 4 here just represents the total number of electrons. There's a pair and then 2 singles, so a total of 4 electrons in the p energy level, sublevel of the second energy level. So electron configurations. You can also go the other direction. You can use orbital diagrams and electron configurations to identify which element they are. So here I have thrown out a crazy looking, don't cheat and look at the bottom, right? I've thrown out a crazy looking orbital diagram there with lots of arrows and spaces to it. I kind of hate these orbital diagrams where they just use dashes like this. It's kind of hard to read them, which is why I kind of encourage you guys to use circles and brackets, like to kind of identify that those are the 2 P's. So this would be written as an electron configuration as 1s2, 2s2, then we've got 2p6 because all of those guys are all together. And then we've got 3s2, that one's filled up. And then the 3p's, it just has 3 single electrons in there, so it's 3p3 would be what that is. So when we take a look at this, there's 15 total electrons. You can either count them as arrows, or you can add up the exponents. 2 plus 2 plus 6 is 10, plus 2 and 3 is 5 more, so it's 15 total electrons. And then you can just look at the periodic table. Okay, which element has 15 electrons to it? And that happens to be phosphorus. I also can confirm that it's phosphorus because phosphorus is in the third row, and it's in the p block. We'll talk about that in a second. And these final electrons here are in the third energy level, which corresponds to the third row of the periodic table. So again, you can kind of go both directions with this. You can either use an element to write an electron configuration, or from an electron configuration, you can determine which element it is. I already said this part, didn't I? Yeah, I did. Anyway, there you go. So noble gas shortcut is a way to write longer electron configurations in a shorter way. The example I've given you here, iron, isn't super long, but it's good enough to use to demonstrate kind of what we're talking about here. So it's called the noble gas shortcut, and what we do is we look at iron itself, and we can take out the part of the electron configuration that corresponds to the last noble gas, the noble gas that comes before that element. So you got to look at the periodic table and kind of trace backwards. You want to find the highest number noble gas that is less than the atomic number of the element that you're using. So noble gases always end in a p6, and so that's another way to kind of figure out if you've got your electron configuration, kind of trace backwards wherever the p6 is, and we can replace all of that. When we do this, we use always a noble gas, and we always put it in square brackets, and then we write the things that come after it. So we're kind of taking apart this blue part here, and we're replacing it with the symbol of that element, which is argon, and then the last little bits that actually make iron different from argon. Keep in mind, there's a couple of things to watch out for. You have to use a noble gas. That's why it's called the noble gas shortcut. You're not allowed to just pick any other element that you want to. It has to come from that far right column on the periodic table. So you're talking about helium, neon, argon, xenon, krypton, radon, one of those guys, but it has to be from that far right side. Cannot use any other type of element for this. And the second thing is that when you're using that noble gas shortcut, you have to include everything that comes after that noble gas's configuration. So down at the bottom here, I've got two kind of counter examples, things to not do. So here was the original electron configuration for iron. Here's an example of one that's not okay. It's nice and short, that'd be great, but this person here used calcium and 3d6. Now calcium is indeed this particular electron configuration through the 4s2, but you're not allowed to do that because calcium is not a noble gas. The one on the bottom here, it's right in the sense that it's using argon, so it replaced the correct thing there, but it missed something. You have to include everything that comes after that P6, so it has to have the 4s2 in there as well as the 3d6, not just the last thing. It has to include everything other than the argon. So there you go, a couple of examples on how to use the noble gas shortcut. Especially for things that get up into the 4th, 5th energy levels, noble gas shortcut is very much a time saver. If you're in the 1st or 2nd energy level, don't even bother. You might as well just write it out. Okay, let's talk about some patterns here. Once you kind of get the hang of these patterns, you'll see that there's actually a lot quicker ways than writing out every single electron. Once you start to figure out what they are, the periodic table itself is arranged in terms of electron configurations because it's arranged in terms of energy levels and sublevels, so that's kind of nice. Each block of the periodic table corresponds to the highest energy sublevel in that atom that's being filled. So for example, the first two columns on the left, we call those the P block. There's the S block, nice English. The S1 and the S2 are both being filled when we go into that particular range. Over on the right here, we have a region called the P block. Everything over on this far right side, except for helium, which is sneaking out up here. Everything else in this main block over here is something that's filling up in the P sublevel. At the center block, the transition metals as we call them, are all elements that are filling up the D block or the D sublevel. And then the F block, those elements down at the bottom that we sort of ignore all the time, those are the F block. Sounds like jail, doesn't it? I'm located in cell block D. But in terms of all these guys, the ones at the very bottom are the ones that are filling up F sublevels, and those got to be very high energy levels to be finding an F. We don't deal with F block even that much in Chem 1, so don't stress about them too much. So let's take a look a little bit closer in terms of how these patterns work themselves out. The nice thing is the columns this way, columns again are vertical. Columns correspond to the number of electrons in that sublevel. Is it column 1 or column 2? That means there's 1 electron in column 1, 2 electrons in column 2. The rows are lefty-righty. Rows go across this way like you'd row across a lake, right? Rows go this way, and the rows correspond to the energy level. So first row is first energy level, second row is second energy level, third row is third energy level. So as we break this apart, everything in the first column is going to have an electron configuration ending in S1. They're in the S block with 1 electron, so they would end in an S1. Second block, these are all S2s. They've got the first arrow and the second arrow, so that's why we would write those as S2s. And then as we go down this way, across, in terms of the rows, we can actually say what the address is. So for example, if we're talking about this element right here, It's in the second row S1 column, so its electron configuration has to end in 2s1. Right next to it, this one has to end in 2s2, second row in the second column, and those are lithium and beryllium. If we keep going down, you can see that that pattern continues, that we've got 3s1 and 3s2. This is sodium and magnesium. These guys have 1 electron in the third energy level, S sublevel, or magnesium has 2 electrons in that third energy level, S sublevel. And it continues on down anywhere you go in this particular range. You can simply count on down. If it's in the first column, it's an S1, count down the number of rows, and you can say this one ends in a 5s1, or if it's in the second column, you can count all the way down to the bottom and say it's 7s2. This saves you some time. 7s2, by the way, is, I think it's barium. No, it's whatever comes after francium. Dang, it's all the way down there. Rather than trying to count up all of those electrons, it's going to have 88 electrons, this one down here. Can you imagine how long it would take you to count all the way to that point? As opposed to just looking at it going, oh, it's got to end in the S2, so I know exactly where that is. Okay, moving over to the P block. P block follows a very, very similar pattern, so I'm going to kind of move through this quickly. It's a little bit more than the S1, S2, because remember there's 3 orbitals and a total of 6 electrons that can be in that P block, so we have to kind of move all the way across here. The first column is 1 electron in the P sublevel, then there's 2, 3, 4, 5, and imagine that 6. The noble gases, like I said earlier, all end in a P6, a full P sublevel. All of those electrons are paired up. So again, as we go down vertically, other than the top one up here, this is helium. Remember, helium's too small to even have a P sublevel, but all the other ones, you can use that same convention where you can figure out which row it's in, and that's going to give you the address of that last electron where they are. So if we follow across the top there, it's going to be 2p1 and 2p2. Those are boron and carbon. We jump all the way over to the end of that. When we get to the end of this first row, that's neon, 2p6, where it's completely filled up. And you can start to do this as you go down. So it doesn't really matter where you are, as long as you know what the column it's in, and then you know the row that it's in, you can kind of figure out how these electron configurations are going to end. And then it's a simple matter to work backwards from there. So again, make sure that you count carefully, and especially over here, don't forget to count this row. This row still counts. A lot of students miss that, and they kind of start counting here, 1, 2, 3, or something like that, and it can cause you to make some errors. So make sure to count helium's row. That's row number 1 as you count all the way down. D block does exactly the same thing, where it's the number of columns corresponds to the number of electrons in the D sublevel, but there's a trick here. Remember, there's energy level overlap. So that means that the 4s is going to start to fill before the 3d, which means that we have kind of a weird energy level number in here as this goes. So again, the columns make perfectly good sense, D1, D2 through D10. That makes good sense, but it's the energy level number that's a little bit off. So the 4s1 and the 4s2 fill up first because they're in that first row, and then it backfills down to fill the 3d. The 3d is such an expensive energy level that those electrons will sneak up into that 4th energy level first and fill up that small apartment. So again, backfill, they're 1 row behind. So again, it's a little bit of a pattern. The pattern makes sense from left to right. You just got to remember that the energy level is 1 less than you would predict that it would be. And again, this fills up for pretty much anywhere that's in there. You can count them over and figure out how it ends. Kind of nice. I'm not even going to talk about F block because F block's just crazy. We're not going to do that in here very often. If you want to figure out F block, go look it up somewhere else. We can deal with it later. So luckily for you guys, you don't have to memorize this pattern, of especially the energy level overlap. Like, when is it the 3D and when is it the 4S? Remember, we've talked about the arrow diagram before. It works just as well for electron configurations as well, and it shows that pattern of overlap. So, for example, this part that we were just talking about and how the D energy level fills up, it's in there. When you take a look at how that arrow diagram fills up, after the P sublevel fills up, the S sublevel fills up, not the 3D. And then the 3D fills up, followed by the 4P. It jumps back up to that other energy level. So it is a little bit strange. So again, if you're not sure what it's going to be, like you're looking at something that's in the D block and you can't remember quite how that works, look at the beginning of the row. That's this hint down here. Find something that's from the very beginning, that very left side that's in the S block, because that will give you the right row number. You can find the S block then here, like, okay, it's a 6S, and then what comes after 6S, then you can kind of follow around and figure out what comes after it. So for using the arrow diagram quickly, it's kind of a nice way to be able to kind of work backwards. Once you have the address of a particular element, you can use the arrow diagram to then construct the rest of the electron configuration. So number one, you want to use that kind of address method. Use that periodic table to figure out what column, what block, what row it's in, and figure out the ending of your a particular electron configuration. The next thing that you do is you look in your arrow diagram and figure out where it is. So is it something that's in the D block? Is it something that's in the P block? Is it in the S block? Where is it? Look locate that ending there in your periodic table and or in your arrow diagram and figure out where that is. Again, if you're in the D block and you're not quite sure, go to the beginning of that row, which has an S block element, and find that. And then you'll know that, like, if you're in the D block, I don't know if it's 4D or 3D, well, go to the beginning of the row. Is it 4S or 5S that starts that row? And that will help you kind of figure that out. And then all you have to do from that point is kind of fill in everything. So if I know I'm in the 3D range, then all I know is that, okay, I'm ending in the 3D row. That means everything else up to that point is going to be full. All of those are going to be full. And then I just pop that 3D ending on the end. So here's an example of how we can work this out. So I'll have you write the electron configuration for cesium, number 55. Number 55 is actually over there on the left side, so find it on your periodic table. It's actually in the S block. So here's how I would do this. Number one, I'd locate it. It's over in the 6S1 position, so it's way over on the left side, down at the bottom, and it's a pain to have to try to write out 55 electrons to figure out where that is. So the next thing I'd do is I'd find 6S over here in my diagram. There it is. So I know it's in the 6S position, so find 6S in the arrow diagram. And then I know that everything else is going to be full. Follow the arrows as you block down. So 1S is full, 2S is full, go to the top 2P, then I go to 3S, then I go to the next one 3P, 4S, then I go to 4D, 3D, etc. So everything's going to be full. So it's going to be 1S2, 2S2, 2P6, etc., except for the very last thing. That very last thing, the 6S, you're going to end it the way it looks like it should be ended based on the periodic table. So here's what it would look like. 1S2, 2S2, 2P6, 3S2, 3P6, 4S2. Oh my gosh, okay, so I got all the way through this arrow. Then the next part, I jump up to the top of the next arrow, and this is where you got to be careful about the arrow overlap. So this shows you what that energy level overlap is. It's going to be 3D, 4P, and then 5S will be the ones that fill up next. So these are all full as well, so you end up with 3D10, 4P6, and then 5S2. So be very careful, don't just kind of run through these. Make sure you check for those overlaps. So I'm at the bottom of this row. Now I pop up to the top of the next row, which means that 4D is going to fill up next. There it is, 4D10, 5P6, and then I'm going to end it with my address, which is 6P1. So that's a faster way to write that out rather than starting at the beginning and trying to keep track of how many arrows you have and did you get up to 55. So a little bit faster to kind of work backwards from the address method and the arrow diagram. All right, so electron configurations, sort of in summary here, they are by far the shortest way of representing the distribution of all of these electrons throughout the electron cloud in terms of all the different distinctions in terms of where they are. They're no longer just out there. They're sort of in this energy level, this sublevel, etc. So electron configurations tell us every electron's location. They kind of summarize it up like we say P6, but it does tell us that there's that particular sublevel is completely full, or that particular sublevel maybe has some room in there. But from that electron configuration, you can determine energy levels, that's the coefficient, the sublevel, that's the letter, and the orbitals, because you know that each letter has a couple of orbitals to it, and then you can figure out which electrons are in there. Is it 2, is it 4, is it 6, or is it 10, depending on whether it's full or not. It's based on orbital diagrams. So every time you've got an electron configuration, there's an orbital diagram behind it. And if you like drawing orbital diagrams better, if that's easier for you to understand, you can always start with an orbital diagram and then summarize it with an electron configuration. You just don't have to once you understand what the patterns are. So again, the energy levels are the numbers, the letters are the sublevels, and the exponents become the number of electrons total that's in that sublevel. Some methods that we can use to make electron configuration writing easier. Number one, you can draw that orbital diagram first if you want to. Not necessarily required, but you can. Number two, the noble gas shortcut. If you can use that accurately, that's always a good thing. And again, that helps you kind of eliminate a wide variety of a long electron configuration by replacing it with a noble gas in square brackets. If you know how to use that periodic table with the pattern, sort of the address method, if it's in the P block, third column, fifth row, that can also make it a lot faster, especially if you use it in conjunction with the arrow diagram. So all of these things together are ways that we write electron configurations. 1s2, 2s2, 2p6, 3s2, 3p6. Oh my gosh, you start saying it in your sleep, right? All right, there you go. I will see you in class tomorrow where we'll be writing some more electron configurations and how we can figure out ions, how we can figure out bonding, how we can figure out if something's excited or not based on these. Have a good day.